Good morning, Internet. I am Matt Booyak, and in this video, we're going to be taking a look at the problem that I've been teasing, or perhaps avoiding, for the last 3 days, the 44th problem from the Project Euler Problem Archive. Now, as I just mentioned, I first tried solving this problem 3 days ago, but had some difficulty coming up with an algorithm that was efficient enough to solve the problem in a reasonable amount of time. I did eventually succeed, and we'll be looking at that approach tomorrow. But today, we're going to look at my failure. That is, the algorithm that was too slow. Now, normally I wouldn't dwell on my mistakes, but this one I think is particularly instructive because the algorithm isn't obviously bad. In fact, it's quite typical of the kinds of algorithms that I've shown on this channel all the time. Now, that alone wouldn't be enough to warrant a separate video. I've made plenty of interesting mistakes that have never seen the light of day. But then I received an interesting suggestion from a viewer on my video for problem number 45. Jacob has a method for efficiently determining if a number is pentagonal or not. Just by chance, problem 45 also deals with pentagonal numbers. And so I tried applying Jacob's approach to my original slow algorithm to problem 45, and it makes it just fast enough that I considered it worth presenting. So, what is this problem? Problem 44 asks us to find two pentagonal numbers, p sub j and p sub k, such that their sum and difference are also pentagonal. And it gives this expression here for the nth pentagonal number. Specifically, we are asked to find the solution such that the difference of p sub j and p sub k is minimized, and it gives that value as d. Now, fun fact, if we had been asked to find or minimize the sum of p sub j and p sub k instead, this would be a much easier problem, even though the solution would be exactly the same. Ponder that riddle for just a moment. So, the approach that we're going to take to this problem is going to be to iterate over possible values of d and p sub j, pentagonal numbers that is, and for each pair we're going to add them to get p sub k and check that that value is pentagonal. If it is, we'll then add p sub j and p sub k to get their sum and check that that is pentagonal. And if all four values are pentagonal, we have our solution. One caveat to that is that we have to make sure that we're iterating over d as our outermost loop. That will guarantee that d is minimized, which is required. Note that this is also the reason why we're iterating over p sub j and d as opposed to, say, p sub j and p sub k, because we can't guarantee that d is minimized if we're iterating over these two values instead. So with all that in mind, let's get to writing some code. So as usual, let's copy our template directory to make our problem directory, enter our problem directory, and open our main.cpp. So first we'll need our pentagonal numbers, call them d, p sub j, p sub k, and their sum. We'll need indices corresponding to d and p sub j. We'll make d the ith pentagonal number and p sub j, as you might expect, the jth pentagonal number. Then we'll iterate over possible values of I. So that's going to be I will start at 1 and go up to infinity, one at a time. Because this is an infinite loop, we'll never actually get to these last two lines. As soon as we find our solution, we'll just return directly from that point. Now we need to be able to calculate d from I. If we go back to the problem description, you might recall this expression here, which we can use to calculate the nth pentagonal number. So let's create a little helper function to do exactly that. Say int64t get pent. And that's just going to be return n times 3 times n minus 1 all over 2. One note that I will make is that though the indices are typically quite small compared to the pentagonal numbers themselves, this calculation can overflow a 32-bit integer if you're not careful. And so I made this argument a 64-bit integer just to avoid that problem. Okay, so let's say d is equal to get pent I. And now we'll want to iterate over possible values of j. So we'll say for j is equal to 1, j is less than question mark. For now, let's just put in a placeholder. We'll say calc upper bound plus j. And actually, let's make this less than or equal to. OK, so now let's calculate p sub j from j. So we'll say get pent of j. And then we can calculate p sub k by just adding p sub j and d. Next, we want to check if p sub k is pentagonal. So we'll say if not is pentagonal p sub k, then continue. That is, just try the next value of j. If it is pentagonal, let's print out our partial solution. As you may have heard me mention a couple times, this algorithm is kind of slow. And so printing out a partial solution will give us some sense of the progress that the algorithm is making. So we'll say printf %ld plus %ld is equal to %ld. And that's going to be d, p sub j, and p sub k. Then we'll calculate the sum of p sub j and p sub k and check to see if that is pentagonal. So we'll say if is pentagonal sum, then we have our solution. So we'll say printf, and we only need the first value, but it's kind of satisfying to see all four and see that they actually do have the desired properties. So I'm going to print out all four of them instead, and that's going to be d, pj, pk, and their sum. And from there, we can just return 0. Okay, so I think you'll understand what I meant in the intro when I said that this algorithm isn't obviously bad. Sure, it's a brute force approach, but that's quite common of Project Euler problems. It also appears to be what we would call an order n squared algorithm, which just means that the running time is roughly proportional to the square of the maximum value of I. And we normally like to avoid n squared algorithms, but again, not too uncommon for Project Euler problems. So where does this algorithm get into trouble? And in order to understand that, we're going to need to finish our implementation. starting with this function, calc upper bound. It may not be immediately obvious that this upper bound even needs to exist. If we go back to the problem description and take a look at the example values for pentagonal numbers, you may notice that the difference between them is increasing as they increase. And if we could prove that that was the case, we could show that eventually the difference between two consecutive pentagonal numbers will grow larger than any particular difference value. And that will give us our upper bound. To make that notion a little bit more precise, we're going to have to do some calculations. So let's open up our analysis file. So in order to calculate our upper bound, let's recall that the nth pentagonal number is given by n times 3n minus 1 over 2. And that's just going to expand to be 3n squared minus n over 2. We can also calculate the expression for the n plus first pentagonal number. So that's going to be equal to n plus 1 times 3 times n plus 1 minus 1 all over 2. And that will expand first to n plus 1 times 3n plus 2 all over 2. And then to 3n squared plus 2n plus 3n plus 2 all over 2. And we can combine these terms, and that's going to give us 5n plus 2 over 2. Okay, so now we can take the difference of these two expressions. So we'll say Pn plus 1 minus Pn is going to be 1/2. We'll factor that out first. And then we'll have 3n squared plus 5n plus 2 minus 3n squared minus n. Okay, well, we'll see that the 3n squareds cancel out. So we have this. We have a double negation here, so then we end up with plus n. So this becomes 6n. And then we can take half of that is going to give us 3n plus 1. So we have a nice, neat expression for the difference between the nth pentagonal number and the n plus first pentagonal number. Going back to the problem description for a moment, if we look at the third pentagonal number, 3 times 3 plus 1 is 10. So we would expect the difference between the third and fourth pentagonal numbers to be 10. And in fact, that is the case. Okay, so now we can just say that D has to be greater than or equal to 3j plus 1. And that's because the smallest difference between between p sub j and p sub k occurs when k is equal to j plus 1, in which case the difference will just be 3j plus 1 from the calculations that we just did. Then we can solve for j, and we get that j is less than or equal to d minus 1 over 3. And that's going to be our upper bound. So let's go back to our program here. And we'll say in 64t calc upper bound in 64t diff. And we're just going to say return, and that's going to be d minus 1 over 3. So diff minus 1 over 3. Okay, so we have just one more thing that we need to implement before we can test our algorithm, and that's this function here, is pentagonal. Now I'm going to start by showing you the original implementation that I came up with for is pentagonal, and it's based on an algorithm called binary search. And the idea of binary search is you have some large list of items which are sorted in ascending order, and you want to find out if your item is somewhere in the list. And you start by checking the middle item and comparing that to yours. And if, for example, it's greater than your item, you know that your item must be in the lower half of the list. So you ignore the larger half and focus on the lower half, and again examine the middle item in that subsection of the list. And you just keep repeating this process, narrowing down your range of search until you get down to just one item, and then it's trivial to check if that is the item that you're looking for or not. So that's the approach that we're going to take for our first pass at is pentagonal. So we'll say bool is pentagonal, int 64t. It's going to take integer p, and we're going to need a large list of pentagonal numbers up to and possibly including the value p. And we don't want to have to reinitialize this list every time. That would be extraordinarily inefficient. And so we're going to declare this as static, which means that it persists across multiple invocations of is pentagonal. And we're going to put that in a vector, and we'll just call that pence. Okay, now we need to initialize pence with pentagonal numbers. So we'll say while either pence.empty or pence.back is less than p. Then we're going to add new elements to the list. And we'll just do that by saying pence.pushback get pence.size. And just to make sure that this is the correct argument, you can consider the case where pence has a single element, which is just 0, which is the 0th pentagonal number. The size will be 1, and so then we'll get the first pentagonal number and add that to the end, which is exactly what we want. Okay, so this will make sure we have all the pentagonal numbers we need. Note that most of the time we will get here and have already filled out the list, and so we won't even execute any of this. Then we need to do our actual binary search. And we're going to do this using the method lower bound, which basically does a binary search to find the first element that is at least as large as the one we're looking for. It could be larger, or it could be that element itself. And we need to give it iterators to the beginning and end of our search range. So we'll say pence.begin, pence.end, and we're looking for p. Now, this function does not actually return the value itself. It returns an iterator to the value. So we need to dereference that. And then we want to compare that to p to see if we have found the alleged pentagonal number that we're looking for, or if we found some other value. And then we'll just return the result of that comparison. We'll need to add a few includes up here. We need to include vector, and we need to include algorithm. Algorithm is where that lower bound method is declared. Okay, so now we should have a complete implementation. Let's see how it performs. We'll go back to our shell and make, apparently there's been a minor mistake. Pence should have a size function. Oh, I didn't actually make it a function. I just used it as a member. Okay, there we go. We'll make, and we can execute. And there we go. And there we go. And we're still going. And it's going to take about 10 minutes before we finally get our answer, which is a bit longer than I would like to wait. So let's go ahead and stop that and think about why this algorithm struggles. And the first reason is something called cache coherence. The idea is that when you're reading from memory, most of the time the processor is not actually reading from memory, it's reading from a cache. The idea is that most likely if you're reading from a particular memory address, you probably are interested in reading other values in the same range of addresses. And so when you read from memory, you don't get just one value, you get a whole range of values. Usually something like 64 bytes referred to as a cache line. And so as long as you are accessing memory values or memory addresses in sequence or all around the same location, you'll be hitting the cache most of the time, which will be very, very fast. But if you're hopping around a lot to different memory addresses, your performance is going to be worse. And unfortunately, hopping around a lot is exactly what binary search does. If you think about it, we're starting in the middle, then we're hopping over here, then we're hopping over there. And every time, especially for a very large array of values, we're probably missing the cache most of the time. And so our performance is going to be very poor. But to be honest, if that were the only problem with this approach, we would probably still be okay. To get a hint for the real problem with this algorithm, let's take a look at this log here and some of the values that we're seeing for p sub j and p sub k. Let's see, this value in particular looks like it's 14 billion or so. And I think some of these other values are even larger. It looks like almost 60 billion here, quite large values, even though our value for D is still relatively small, only 500,000, almost 600,000 or so. And to understand why that is, let's go back to our source, and in particular to take a look at this calc upper bound function and how it's used down farther down. So we'll see here that the result of this function is proportional to diff. Going down to where the function is actually used, we see that the argument here is d. That's what we expect. But d is proportional to I squared because we get d by calling this get pent, which squares I. And so if our upper bound is proportional not to I, but to the square of I, our algorithm isn't an order n squared algorithm. It's actually an order n cubed algorithm, which is even worse than order n squared. And this is the fundamental reason why this approach doesn't perform very well. As I said, if it were only a matter of cache coherence, we could survive that, but order n cubed, we simply cannot. Now, fortunately, we don't have to end it here. I still managed to find a way that we can get to a solution using this method, thanks to the suggestion from Jacob for an alternate implementation of is pentagonal. But in order to show you how that works, we're going to need to jump back over to our analysis file. So the key to Jacob's method is to take the expression up here for the nth pentagonal number and to solve for n and to consider the conditions under which we get an integer for that value. That is, what do you have to put in as a pentagonal number to get an integer index as a result? So let's do that. Going down here, we'll start with p is equal to n times 3n minus 1 over 2. And we can do some basic algebraic manipulation here to get 2p is equal to 3n squared minus n. And then we can rewrite that as 3n squared minus n minus 2p is equal to 0. And this might already be setting off some alarm bells for some of you. You'll notice if we look at this from the perspective of n, this is a quadratic equation. And we have a standard go-to solution to solve quadratic equations. That is the quadratic formula. If we go back over here, you may recognize this. I expect many of you have learned this at some point in your career. Minus b plus minus the square root of b squared minus 4ac over 2a, where a is the coefficient on the quadratic term, b is the coefficient on the linear term, and c is the constant coefficient. One note is that we won't need the minus here. That would give us a negative number, at least in our case. And so since we know that our index is not going to be negative, there's no such thing as negative pentagonal numbers, we can ignore that case. Okay, so let's just, for reference, copy that over here. We're going to say n is equal to minus b plus the square root of b squared minus 4ac all over 2a. And in our case, we have a is the quadratic term, so that's going to be 3. B is the linear term, so that's going to be negative 1. And c is the constant term, which is going to be negative 2p. So then we can substitute those into our formula, and we get negative 1. Oops. Negative 1, so that's going to be just 1, plus the square root of negative 1 squared, so also 1, minus 4 times 3 times negative 2p, all over 6. That's 2 times a. And we can clean this up a little bit here. You can see 2 times 3 times 4 is going to give us 24. The minus signs will cancel out. So we get 1 plus 24p. Okay, so from this, we know that in order for p to be a pentagonal number, the result of this formula has to be an integer. And so the first thing we'll notice is that 1 plus 24p has to be a perfect square. If it is not a perfect square, this will give us an irrational number, and no amount of adding or dividing by integers will turn an irrational number into an integer. Simply cannot be done. And so this must be a perfect square. So that will be our first check. 1 plus 24p must be a perfect square. Then we can take the result of that square root and add 1, and the result must be divisible by 6 in order to get an integer. And so that will be our second check. Now, looking at this, you may think that this is not a particularly difficult solution to come up with. And you might ask, Matt, how come you didn't consider this approach? And the answer, to be honest, is that when it comes to floating point numbers, I'm afraid. Floating point numbers do not do what you think they do. Floating point numbers are evil. Floating point numbers, you can do a calculation that should give you 3, and instead it gives you 3.00000000001. And then you compare it to 3 and it says, nope, that's not 3. But it gets even worse. There are integers that can be represented as a 32-bit signed number that cannot be represented as a 32-bit floating point number. And so if you convert from one to the other, you just get some other integer. It's close enough. And that's how you have to think about floating point numbers, is that they're kind of an estimate for your answer. They're not real numbers in the mathematical sense that have infinite precision. They are an estimate of what your answer should be. And so with that in mind, and understanding that perhaps there be dragons, we're going to use floating point numbers. I would be the first to concede that my, shall we say, paranoia when it comes to floating point numbers might be a little bit overblown, but only a little. Okay, so we're going to write an alternate implementation of is pentagonal. And as before, it's going to take a 64-bit integer. And we want to check if this is, or rather if 1 plus 24p, going back over to here, is a perfect square. And so the idea is that we're going to take the square root, convert that to the nearest integer, square that, and see if we get back the number that we started with. So let's say int 64t disk. So that's short for the discriminant, which is the fancy name for this value here, 1 plus 24p. That is the discriminant. And so we'll say disk is going to equal 1 plus 24 times p. And then we'll say, actually we'll say int 64t disk sqrt, so that's the square root of the discriminant, is going to be equal to round L of sqrt L of disk. So these L's, this Squirtle here looks kind of like a Pokemon, but the L just means that we're using the more precise, the long version of the function. And so as I mentioned in my rant about floating point numbers, you lose some precision even converting between integers and floating points of the same size. So we definitely, if we're using 64-bit integers, want to be using at least 64-bit floating point numbers as well. So that's what this round L and square root L are indicating. Okay, so then we'll say if disk sqrt times disk sqrt is not equal to disk, return false. That is, it's apparently not a perfect square, and so we do not have a pentagonal number. Okay, so now we need to do our last check of seeing if the square root of the discriminant plus 1 is divisible by 6. So we'll say return disk sqrt plus 1 mod 6 is equal to 0. That is, if it divides evenly, then we do in fact have a pentagonal number. Okay, so this should be our answer. So let's go back over to our shell. And we will make. Actually, I can already tell you this is not going to work. I just remembered I'm going to need to add some additional includes, in particular math.h. Okay, now make and solve. You recall, oh, we just went past 500,000. That's how far we made it the last time we ran. You can see it's going much faster than it was before. Already up to 3 million. As you can see, it still takes some amount of time. It is an order n cubed algorithm after all. But eventually, we have our solution. So now let's go back to the archive. And I will need to sign in. Okay, now we can scroll down to problem number 44. And we see that at long last, this does in fact match our answer. Now, before we move on to ending this video, there is one final note that I would like to make. And that is, it's actually possible to hack this problem a little bit. And when I was trying to remember how I first solved this problem, probably 13 years ago now, I suspect that this might be how I solved it. And perhaps many others have done it this way also, which is if you assume that your values of d, p sub j, p sub k, etc. are reasonably sized. Suppose you assume that they are less than 100,000, or less than 1 million, or less than 10 million, and search for solutions with values less than that upper bound. It's arbitrarily chosen upper bound. Maybe you try 100,000, you get no answer. You try 1 million, you get no answer. You try 10 million, you get this answer here. And when you put that number into Project Euler, it confirms that yes, that is the answer. Even though at that point you have no reason for confidence that that is actually the correct answer. Because you've excluded, going back to here, you can see all these enormous values. These all, in theory, would have been perfectly valid candidate solutions. But if you arbitrarily rule them out, you can get to a solution much faster. And I expect that that's probably how I did it when I first solved it. And I expect that many other people have taken that approach as well. Now, tomorrow, I will show you a much more efficient and much more interesting way of solving it. So I hope you'll join me for that.